Let's determine the orbits of a permutation sigma given here. Our sigma is a permutation on S6 because we have here 6 mapping or 6 elements as well. And the orbits are actually sets or subsets of the certain given set, where the elements are related to one another in such a way that the elements are mapped to one another using this given idea. You have for certain A and B element of set A, which is the original set, in this case S6. Let A be related to B if and only if you have here B is a result when we map our A n times. So for some n element of Z. So if we are going to look for the relations or the relationship of A and B as elements of A, and if they are actually, or B is the result, if we're going to map A to or look into the mapping of A as we multiply our sigma n times, so those are the elements of your orbits. Or we can do it like this. We can illustrate it in this manner. So we are going to solve for the orbits. Let's start if we are going to have a sigma of 1. Okay, so the mapping of 1 here, as you can see, 1 is mapped to 5. So we can have it like this. This would mean that 5 is related to 1. Okay, because 5 is 1 is mapped to 5, and yeah, that's the same idea. So since 1 is mapped to 5, so they are related to one another. But we do not stop there, because if we are going to have to do the additional multiplication of our, what do you call this one, our sigma of 1, we are not going to use the sigma of 5, because this will be the process. Of course, if you have your sigma squared as given here, you will have 1, 2, 3, 4, 5, 6. So you have 5, 1, 3, 6, 2, 4 multiply to each other, right? 1, 2, 3, 4, 5, 6, 1, 5, 1, 3, 6, 2, and 4. This is your sigma squared. So you have 1 here. 1 is mapped to 5 from right to left, and then your 5 is mapped to 2. So if you're going to take this the square of sigma and you're using 1, okay, the orbit containing 1, so you will have here to focus now on the mapping of 5, which is now to 2, because 5 is mapped to 2. So 5 and 2 is part in the orbit containing 1. But we do not stop there, because we need to continue. So if we're going to have cube, this is actually just the sigma of this result here. And the sigma of 2, simply focus here, will just return to 1. As you can see, we only have 3 elements for this specific pattern. So we have here the set containing 1, 5, and 2. Since it's a set, we could actually rearrange them, but just for our practice, because the next topic in related to orbits would be possibility of cycle, and for representation of cycle, the order should be correct. Let's have it like that. This is your first orbit. You have 1, 5, and 2. The set containing 1, 5, and 2. So to solve for the next possible orbit, since 2 is already here, because you're already done with 2, let's proceed to the orbit containing 3. And here, orbit containing 3 is just 3 itself. Okay, it ends there. That would mean this is a set containing 3 alone. Next, let's have the orbit containing 4. Okay, so 4 is mapped to 6. Then, if you're going to have the sigma square of 4, that's actually a sigma of 6. So 6 is now mapped to 4. Since if you return to 4, you will have here 4 and 6. Okay, so we have 1, 2, 3, 4, 5, and 6. You already have your 6 here. You already have your 5 here. So we are done. These are now the 3 orbits of this given permutation. You have the orbit containing 1, 2, and 5, or 1, 5, and 2. Again, we could be they could be rearranged because they are under a set. Okay, so we have 1, 5, and 2, or 1, 2, and 5. You have 3, and you have 4 and 6. So this is how we determine the orbits of a certain permutation. And this is very important as we move further into identifying whether these are cycles or not, and other concepts as well. But before we end this, it's good also to understand that our orbits are disjoint sets. Disjoint sets because in the sense that they do not share any element. Because if I talk about orbit, of course, so just like this 1, 5, and 2, it will just revolve around these 3 elements, and it will not touch other elements as well. In other sense, these elements 1, 5, and 2 will also not appear on other orbits. So you have 1, 5, and 2, 3, and 4, and 6, and we can even illustrate it like this. Since you have here 1, 2, and 5, this is your 3, that's your 4 and 6. They're actually disjoint as mentioned, because at the same time the union of all orbits is the given a set S6. Okay, you have 1, 2, 3, 4, 5, 6 as well. Thank you very much for watching.